Hello everyone. I want to start with thanking the organizers for giving me this opportunity to talk here. It's been a nice workshop. I'm going to talk about cosmology of plate-forming ballistic dark matter, which is work based on this paper in collaboration with Vasudev and Rishi in TFR. So why late-forming dark matter? Because there are several possible theoretical particle physics scenarios of dark sector physics where it is predicted that dark matter was not cold until very late epoch, and we want to probe these kind of scenarios, and the best way to do that is using cosmological observational data. Of course, you want to know how late is late here. So here is a timeline that should give you some idea about it. We'll typically try to see what are the new things that would happen if cold dark matter is formed after, let's say, BBN. Okay, so to do that, we conceive a very simple, basic cosmological framework, which we are calling as ballistic dark matter cosmology. So we parameterize it using three parameters. The first one being a redshift, a transition redshift called Z star, which basically separates the radiation phase in the dark sector with the matter phase. So before this redshift, the dark sector was relativistic and collisional, and after this redshift, it converts to non-relativistic and collisionless phase, which is our ordinary cold dark matter. The next thing is what is the duration of this phase transition, and also if we can also allow this possibility that this ballistic dark matter does not form all of the cold dark matter. There could be some part which behaves just like ordinary CDM. So, and in that case, what is the fraction of this ballistic dark matter? So these are the three parameters that I'll be using. So I'll tell you what this cosmology means in the context of the extra relativistic degrees of freedom at the time of BBN, and I'll also try to explain quickly the density perturbation mode evolution in this cosmology and the new effects that we'll see in the matter power spectrum and in the CMB anisotropy power spectrum. So begin with, as I've said, that if you follow the density perturbation, if you follow the background density evolution of this ballistic dark matter, it's separated these two phases. This is a radiation phase and this is a matter phase, and they are separated by this transition epoch. So before this, it is evolving as 1 over A4, and after that, it is evolving as 1 over AQ. So clearly, at the time of BBN, which is somewhere here, this dark sector is totally thermalized collisional relativistic fluid, so that will come towards your N effective, and that gives you the first constraint on this kind of cosmology. So if you take the current constraint on N effective from BBN data, you see it's around delta N effective is around 0.5. And if you translate that constraint into the context of our model in the plane of FBDM and Z star, you see that already a large portion of the parameter space is ruled out. So now the most important thing is the evolution of individual density perturbation modes. As I said, there are two phases there will be two phases in the evolution of the density perturbation. The first one is the radiation phase. The next part is the matter phase. In the radiation phase, it's behaving as a collisional relativistic fluid, which means it will undergo these acoustic oscillations, and you can see that here. And in this case, I have chosen a particular mode in such a way that at this time of transition epoch, it was just crossing this zero line and with the maximum velocity. So in the matter phase, you will see what happens is it grows logarithmically but with a slope which is given by the perturbation at this time at the phase transition time. So you can see for this particular mode, the density perturbation is released at z star with the maximum possible velocity. But this is one extreme case, but there is another, and this also explain. Sorry. And this behavior also explains our name of ballistic dark matter, because this particular modes will be growing with a maximum possible velocities in the matter phase. But there is other extreme cases also possible where the mode was not at the 0 point, but it was at the maximum point, and but the velocity was 0. In that case, in the latter phase, it will not grow at all. It will stay at this minimum point, and in between you can have all these possible scenarios. And if you scan along the K space, you can see that this will be a periodic feature. So that's one thing. Another interesting thing is that for this maximally growing modes, they can eventually overcome the corresponding density mode in the CDM, in the ordinary CDM case. So that already gives you some idea of what can happen in the matter path spectrum, which I'll come to next. Here, the red curve is a plot of this matter path spectrum in this ballistic dark matter scenario. So there are two things here. The first one is there are oscillations beyond some scale. These are just imprints of these acoustic oscillations which the dark sector was undergoing before the phase transition. The second thing is the envelope of this oscillation is above the lambda CDM curve, which, as I have just explained in the previous slide, is because these maximum modes are they eventually acquire more power than the corresponding lambda CDM curves. So that explains these two features in the lambda BDM cosmology. And I should also mention here that this kind of signature is very different from other non-standard cosmologies. For example, warm dark matter or acoustic dark matter, where you may or may not have oscillations, but the envelope of the oscillation is always suppressed relative to the lambda CDM case. So we can also try to see what happens if BDM does not form the 100% of the cold dark matter. So in that case, I have to allow FBDM, this fraction, to be less than 1, and we have to track both the components, the BDM part and the cold dark matter and the CDM parts. So here I'm plotting these transfer functions as a function of K. This orange curve, I don't know if the colors are very clear, but this dashed orange curve is the BDM transfer function, which is a nice sinusoidal oscillation. This blue dashed curve is a CDM transfer function, which is always above the 0 line, but it also shows some oscillatory feature because of the back reaction from the BDM transfer function through the gravitational potentials. So now if you combine them with this with appropriate fractions, you get this solid black line, which of course asymmetric about this 0 line. And when you to compute the path spectrum, you need to square this, and these particular points will give you the consecutive maxima in the path spectrum. Yeah, thank you. These points will give you the consecutive maxima in the path spectrum, and you can also clearly see that there will be some asymmetry in the peak heights. So you can see this particular plot where the 40% of the dark matter is in the form of ballistic dark matter, and there will be some asymmetry. There are asymmetry in the consecutive peak heights in the matter path spectrum. And of course, if you go towards 0 FBDM, which and you eventually, and these oscillations will vanish, and you eventually rederive your normal ordinary lambda CDM case. So we tried to do some preliminary rough analysis to see what is the constraint that you get on this kind of cosmology from large scale structure and CMB data. So this is a comparison, sorry. Here is a comparison of the MetaPath spectrum computed from our cosmology and the WiggleZ survey data. And we can, just from our estimation, we can see that the redshifts below 5 times 10 to the power 4 is in kind of tension with this, with large scale structure data. But of course, I should emphasize that this is just a preliminary analysis and it's not the final thing. So CMB anisotropy path spectrum, we should also expect some changes there. Here you see 3 different curves with 3 different transition redshifts, and they are compared with the Planck error bars here. And this is the TT path spectrum. Also in the TE and EE path spectrum, you can see in all of these curves, the transition redshift of 4 times 10 to the power 4 happens to be the borderline case. So all the redshifts below this will be ruled out by the CMB data alone. This is again a preliminary analysis. Right now we are doing the proper Monte Carlo analysis of our model, and that will give you a more qualitative idea of to what extent our model is valid. So, and this I'll conclude. We have tried to see what if the primitive dark setup was relativistic and collisional, and what happens in the cosmological observations. Because of that, there will be dark acoustic oscillations in the radiation phase, and there will be velocity overshoot effects in the MetaPath spectrum, which will lead to oscillations, and the envelope of the oscillations will be above the lambda CDM curve. And in addition to that, if ballistic dark matter is not the 100% of the cold dark matter, then there will be an asymmetry in the peak heights in the MetaPath spectrum. We also see changes in the CMB anisotropy path spectrum, and right now we are doing the proper Monte Carlo analysis with all large scale structure and Planck CMB data. So with this, I'll stop, and thank you all for your attention.
Thank you.